And today we have the pleasure to have Konstantin STOYCHEV, who is a postdoc at IJCLab. And he will be talking about its PhD results about the structure of exotic nuclei through measurements of magnetic moments of excited nuclei states. So, Konstantin, the stage is yours.
Thank you. Thanks for the introduction, and thanks for allowing me to present my work. And as Louis just mentioned, I will be presenting mostly results from my PhD thesis and a bit of work afterwards as a postdoc at IJCLab. And here's the outline of my talk. I'll start with a brief introduction on magnetic moments, and after that I will go into magnetic moments of isomeric excited states in the nanosecond to microsecond range, and I will introduce two methods, the time-dependent perturbed angular distribution method and the time-dependent perturbed angular correlations method. And I will also show some examples of analysis that we are working on. And after that I will switch to magnetic moments of short-lived excited states in the picosecond range using the time-differential recoil in vacuum method. And I will present the results from the first application of this method on a radioactive ion beam of magnesium-28. And I will discuss briefly about how we're trying to extend the range of the method towards higher Z nuclei. So let's start with the introduction. We're all familiar with the chart of nuclides, where we have all the known isotopes with the stable ones marked in black, and the other ones being radioactive, denoted with different colors depending on their main decay modes. And with horizontal and vertical lines, we have the so-called magic numbers, which were explained by the nuclear shell model, which suggests that the protons and neutrons are occupying different orbitals that are organized in shells, and the magic numbers correspond to the large energy gaps in between these shells. And an active area of research in nuclear structure studies is how these magic numbers evolve when one moves away from the valley of stability towards more exotic nuclei. And one example that I can give is shown here for neutron-rich calcium isotopes, where we have the evolution of the effective single particle energies as a function of neutron mass number with the addition of more and more neutrons. And you can see that different magic numbers may appear and then disappear depending on the evolution of these single particle energies. And the nuclear magnetic dipole moment is especially sensitive to the single particle structure of the nucleus. And the magnetic dipole moment is itself the product of the gyromagnetic factor, also known as the G factor, multiplied by the spin of the nuclear state. And it's given in units of the nuclear magneton. The magnetic dipole moment is generated mainly by the orbital motion of protons and the intrinsic spins of all nucleons. And it's given as a sum over the orbital and spin contributions of all nucleons, weighted by the corresponding orbital and spin G factors, which have different values for protons and for neutrons. And so through this relation, we can see why the magnetic moments are sensitive to the contributions of different single particle configurations to the nuclear wave function. And if we have an even nucleus, of course its ground state spin is zero and its magnetic dipole moment vanishes. But if we add one valence nucleon, we expect that the magnetic dipole moment of the entire nucleus will be dependent on the magnetic dipole moment of this valence nucleon. And this is essentially the extreme single particle model, according to which the magnetic moments of such odd even nuclei would lie along these lines known as the Schmidt lines, which are plotted here on the right for odd proton and odd neutron nuclei. And as we can see, these Schmidt lines can capture the apparent trends in the magnetic moments, although they fail to reproduce the absolute values of the magnetic moments. And that is why usually effective G factors are introduced instead of the free nucleon G factors, where a quenching factor is introduced for the spin G factors that can have different values depending on the different areas of the chart of nuclides. And if we have more than one valence nucleon, there are the additivity relations, which show how the individual nucleons contribute to the overall G factor of the nuclear state. And now with this, we can turn to how to actually measure the magnetic moments of excited states. So we do this by using magnetic fields. When we apply an external magnetic field, the magnetic field interacts with the magnetic dipole moment and forces it to precess around the magnetic field axis with the Larmor frequency, which is proportional to the G factor of the nuclear state and the magnetic field strength. So if we can somehow manage to measure the Larmor frequency, we can then determine the G factor when we know the magnetic field strength. Now, one thing that we need to keep in mind is that we are interested in excited nuclear states, which typically de-excite through gamma ray emission. And if we have a nuclear ensemble of randomly oriented nuclear spins, the gamma ray emission would be fully isotropic with an isotropic angular distribution of gamma rays. And if we can then manage to produce a spin-aligned or spin-oriented nuclear ensemble, this would introduce anisotropy in the angular distribution of gamma rays. Then if we apply an external magnetic field, this would cause the nuclear spin to precess, and so would the angular distribution of gamma rays. And then measuring the Larmor frequency becomes relatively easy by just placing a gamma ray detector and observing the evolution of the gamma ray intensity as a function of time. The next thing that we need to keep in mind is that half-lives of excited states can be very different and can span multiple orders of magnitude. So in order to observe the precession of the angular distribution, we need the period of the precession to be similar to the half-life of the state of interest. And the only way to do that is by selecting the appropriate magnetic field strength. So in the two cases that I will be looking into, for isomeric states with half-lives in the nanosecond to microsecond range, the appropriate magnetic field strengths are about 1 Tesla, which can be achieved either with permanent magnets or electromagnets quite easily. However, for short-lived excited states with half-lives in the order of picoseconds, we need much stronger fields around kilotesla, and those are not attainable by any macroscopic devices. And instead we need to rely on the hyperfine fields that are generated by the orbital motion of the electrons around the nucleus. And here we have an overview of the different methods that are available for measuring magnetic moments depending on the lifetimes of states that they can be applied to. And in the first part of my talk, I'll focus on the time differential perturbed angular distribution and perturbed angular correlation methods for isomeric states in this range. And after that, I'll focus on the time differential recoil in vacuum method for picosecond states, and I'll briefly mention the transient field method here and there. So with this, we can continue to the second stage with the isomeric states in the nanosecond to microsecond range. So starting with the time-dependent perturbed angular distribution method, first thing we need to do is to populate the excited state of interest and to produce a spin-oriented nuclear ensemble. And this is usually done with a nuclear reaction, which can be transfer, fusion, evaporation, or projectile fragmentation. And today I'll only focus on the fragmentation part. So after we produce this isomeric state and the spin-oriented state in the fragmentation reaction, we implant the spin-oriented nuclei in a host, in a foil, at the center of the detector setup, which consists usually of 4 detectors placed at 90-degree angles to each other. And we apply an external magnetic field, which causes the nuclear spin and the angular distribution of gamma rays to precess. And then we can observe the periodic modulation of the gamma ray intensity in the opposite pairs of detectors, shown here in blue and red. And if we then construct a ratio function from these detector intensities, we get something like this, an oscillation pattern. And by fitting this oscillation pattern, we can directly extract the Larmor frequency, from which we can then get the G factor value of the state of interest. And as an example, I will be using some measurements in the region around nickel-68. Nickel-68 has a magic number of protons and 40 neutrons, which corresponds to the subshell gap between the FP shell and the G9 half orbital. And 20-30 years ago, it was quite an interesting region to study, as there was some evidence that nickel-68 might actually be a doubly magic nucleus, because its first excited state is a 0+ state. And you can see that the energy of the first 2+ state is relatively higher than its neighboring nuclei, which both of these are typical signatures of magicity. However, from mass measurements, it was seen that there's only a small kink in the two neutron separation energies, which is not compatible with magicity at n equals 40. And one suggestion that was put forward is as to why the excitation energy of the 2+ state is so high, is that due to the particular ordering of the orbitals in this region, and the only possible way to create a positive parity 2+ state would be to excite simultaneously two neutrons to the G9 half orbital. And studying nickel-68 from the point of view of magnetic moments would have been very helpful at that time. However, it was experimentally very difficult. What was possible to be done was to study this region through measurements of magnetic moments of isomeric states. And in fact, the first TDPAD measurement following a fragmentation reaction targeted exactly the 9.5+ isomeric state in nickel-67. This experiment was performed at Ganil. And the follow-up measurement after this one at Ganil aimed to measure the G factors of G9 half isomeric states in nickel-69 and 70 at NSCL. And I'll now present you the results from this experiment some 18 years later. Here is the overview of the facility at NSCL. We have two coupled cyclotrons which accelerate a beam of germanium-76 to an energy of 130 MeV per nucleon. The beam impinges on a thick beryllium target to produce a wide range of radioactive nuclei. From these, we collected data only on nickel-67, 69, and 70, which were transferred along the A1900 separator and implanted here at the TDPAD setup, which consisted of 4 Sega germanium detectors in the horizontal plane and an electromagnet for the magnetic field. So, continuing with the results. Here is the first for the 9.5+ isomer in nickel-67. Here we have the level scheme depopulating the isomer and the gamma ray energy spectrum. On the right now, sorry, you can see the fit of the half-life of the isomer, which is in agreement with the adopted value. And here you can see the experimental ratio function that we obtained and the best fit of the data, which yields a G factor value of -0.26. And unfortunately, this is actually not in agreement with the previous measurement that was performed at Ganil. We see that there's a factor 2 difference between the two measurements, which is currently not understood well. Still moving on to nickel-69, we have the 17.5- isomer here, the gamma ray energy spectrum, and the fit of the half-life of the isomer. In this case, our result for the half-life is slightly smaller than the adopted value, which we consider that most probably the uncertainty of the adopted value may be underestimated. And on the bottom you see also the experimental ratio function with the best fit of the data and obtain the G factor value. And finally, for the 8+ isomer in nickel-70, we have the level scheme, and we have this time perfect reproduction of the half-life of the isomer, and again the ratio function and the G factor value of -0.31. And now with these results we can compare them to shell model calculations performed with the June 45 interaction, which has a nickel-58 core, so it allows only for neutron excitations, and also with the LMPS interaction, which uses a calcium-48 core and thus allows both proton and neutron excitations. And here we have the present experimental result and its uncertainties, And we see that our result is in agreement with the LMPS calculations using effective spin G factors, while the adopted value from the Ganil measurement is not reproduced by any of the available calculations. So this lends more confidence to our present analysis. Next, for nickel 69, the present result is in agreement again with the LMPS calculations, but this time for the free nucleon G factors, although it is also quite close to some calculations with effective G factors when proton excitations are not allowed. And the similar situation is also in nickel 70, where the experimental value is in agreement with various calculations with the effective G factors, but it also lies very close to the LMPS calculations with free nucleon G factors. And this situation is very similar also to the older case of the G9 half isomeric state in nickel 65, which was measured 20 years ago, again with the TDPAD method. And in this case here we have the results from theoretical calculations with effective and with free nucleon G factors as a function of the particle Hall excitations allowed in the calculations. And in green we have the experimental value, which for when only one particle Hall excitation is allowed, which will be for the neutrons, the effective calculations with effective G factors are very close to the experimental value, but after allowing also for proton excitations, we can see that the calculations with free nucleon G factors are also able to reproduce the experimental result. So two main conclusions we can draw from these results. First, that the Z equals 28 shell gap is quite fragile, and indeed we most certainly need proton excitations to properly describe these excited states in nickel isotopes. And the second point is that possibly when we perform shell model calculations in a large enough valence space, we are able to capture most of the correlations that are relevant to these states, and thus we can avoid the addition of quenching factors in the calculations. And these results are currently being prepared for a publication, and we're working on the complete interpretation from the theory side. And from this point, I can switch to the second method I would like to briefly discuss, which is the time-dependent perturbed angular correlation method, or TDPAC. Experimentally, it's very similar to TDPAD, with again applying an external magnetic field and having a setup of typically 4 germanium or 4 detectors at 90-degree angles to each other. Only in this case we measure not the angular distribution but angular correlations between the gamma rays transition populating and depopulating the excited state of interest. And once again we have a slightly different ratio function to obtain the Larmor frequency in the end. So the TDPAC method has some advantages over TDPAD, such as the fact that this method does not need any initial spin orientation, because we obtain our orientation from registering the populating gamma ray transition. And this has some advantages because it allows to access isomeric states populated following beta decay, and also it allows to access shorter half-lives. With the TDPAC method, one could reach down to a few nanoseconds, or measure the magnetic moments of isomeric states with half-lives of a few nanoseconds. Of course, the method has also disadvantages, the main one being that of course now we need to work in coincidence mode, which requires more statistics. And the example that I would like to show about the TDPAC method is a recent measurement we performed at the Long-Grain spectrometer at IJCLab Grenoble, where they have a nuclear reactor with the highest continuous neutron flux of 10 to the 15 neutrons per second per centimeter squared. And at IJCLab they place a fission target right next to the reactor, and neutron-induced fission occurs. The fission fragments then recoil out of the target and are directed towards the detector setup via a dipole magnet and an electric condenser. And at the detector setup, we once again apply our external magnetic field and have the for detector setup. The example measurement that I will be discussing is one on Yttrium 98, which lies very close to the region of the onset of deformation at n equals 60, which is evidenced here by the sudden increase in the mean square charge radii. And in particular, we're targeting the magnetic moment of the 4- isomeric state with half-life of 35 nanoseconds. Here you can see the gamma ray energy spectra for this nucleus and the partial level scheme. So selecting the populating and depopulating transitions of the 4- isomeric state, we can obtain this preliminary ratio function, where you can clearly see one full period of the oscillation before around 100 nanoseconds, where most of the isomeric state has decayed. And this is, of course, preliminary work that I'm currently working on, and hopefully we'll have more final results soon. And with this, I'd like to summarize the first section of my talk. So I presented the TDPAD and TDPAC methods with some examples on the nickel isomeric states and the isomeric state in the Yttrium 98. And something that I did not mention so far is that both the TDPAD and TDPAC can be also applied to measure the electric quadrupole moments of isomeric states, and in fact we have already submitted a proposal to measure the quadrupole moment of this 4- isomeric state, again with TDPAC at ILL. And in addition, we also have a program to study nuclear structure around tin 132 with several measurements on isomeric states with both methods at RIKEN and ILL. And finally, there is also a dedicated TDPAC setup that has been developed for the Zolde decay station, and the first tests are supposed to happen, I think, this year, so one can expect more interesting experiments on radioactive ion beams in the future at Zolde. And now we switch gears to short-lived excited states in the picosecond range. So I will be focusing on the time-differential recoil in vacuum method, and as I mentioned in the beginning, and for such short-lived excited states, one needs to rely on the hyperfine fields of electrons orbiting the nucleus. For ions with a single S-shell electron, the hyperfine field experienced by the nucleus is given by this equation on the right, and typically the magnetic field strength is highest for hydrogen-like ions, and they are usually used in the TDRIV experiments. Once again, we first have to populate and spin orient the state of interest, which is done by a nuclear reaction in the target foil. Commonly, Coulomb excitation is used for this purpose. Then the excited nuclei recoil out of the target foil into the vacuum as ions with one or more electrons. And under the influence of the hyperfine interaction, the atomic and nuclear spins couple to a total spin F, and the nuclear spin begins to precess around the total spin with a frequency that is once again proportional to the G factor of the excited state and the magnetic field strength of the hyperfine field. The interaction between the hyperfine field and the nuclear spin is defined by the distance between the target foil and the secondary stopper foil. Upon reaching the second foil, the interaction is interrupted, the atomic and nuclear spins decouple, and the precession stops, which fixes the direction of the nuclear spin in place, and so it also fixes the direction of the angular distribution of gamma rays. So if we can change the distance between the target foil and the stopper foil, we essentially would fix the nuclear spin direction in a different position, and we would observe a different angular distribution of gamma rays. So we can sample the angular distribution of gamma rays by changing the distance between the two foils. If we also register light reaction fragments from in a particle detector, we can then use particle gamma angular correlation to enhance the anisotropy of the observed gamma rays. And by, again, forming a ratio function from these angular correlations, we can get an oscillation pattern that we fit, and we can obtain the absolute value of the G factor of the excited state. In this type of experiment, typically most of the beam does not interact with the target, but is still stopped in the stopper foil. And in stable beam experiments, that is not a problem because it does not interfere with the measurement itself. However, for radioactive ion beams, implanting a bunch of radioactive ions in the stopper foil increases a lot the gamma ray activity in the setup, and that could be very problematic for the performance of the detectors. So instead, a modification of the method was proposed some years ago that would exchange the thick stopper foil for a thin foil that simply resets the electron configuration and allows all the unreacted radioactive beam to simply pass out of view of the detector system. And this comes at the small cost of a slight reduction in the amplitude of the observed ratio function. And this modified version of the TDRIV method was successfully applied on a stable beam of magnesium-24 in an experiment here at the Auto facility in Orsay. And of course, the next step was to perform a test on a radioactive ion beam, which was magnesium-28 experiment at IJCLab. Magnesium-28 was chosen as the test case because it lies close to the island of inversion around magnesium-32, where the n equals 20 magic number disappears. And it was thought that the transition towards the island of inversion is quite abrupt, with magnesium-30 lying outside and magnesium-31 lying inside the island of inversion, which was also supported by theoretical calculations. However, more recent experimental results and theoretical calculations indicate possibly a much smoother transition towards the island of inversion. And this hypothesis can be tested by measurement of magnetic moments of excited states, in this case the G factors of the 2+ states in even magnesium isotopes. Here we see the pure SD shell model predictions for these G factors in a solid line, and with these points are the predictions from the older calculations by Otsuka with the SDPF. If we assume that a smoother transition towards the island of inversion is the case, maybe we can already see a deviation from the pure SD shell calculations at magnesium-28. So the goals of the TDRIV measurement of the G factor, the 2+ state in magnesium-28, were to test the feasibility of the method on a radioactive ion beam and also to probe the boundaries of the island of inversion. As I mentioned, the experiment was performed at the Zolde facility at CERN, which lies here, and gets high energy protons from the proton synchrotron booster. 1.4 GeV protons impinge on a production target where they induce fragmentation, spallation, and fission reactions that produce a wide range of radioactive isotopes. And these radioactive nuclei effuse out of the target to be ionized and mass separated before being sent towards the experimental setup. In the case of magnesium-28, the magnesium-28 beam was sent towards the high Zolde facility to be post-accelerated and then directed to the mini-ball setup. Here we can see the photo of the mini-ball setup, which consists of 8 triple clusters of germanium detectors, here positioned around 90-degree scattering angles to where the maximum anisotropy of the angular correlations is expected. In the vacuum chamber, we also have the CD double-sided silicon strip detector for particle detection and the mini-ball plunger device, which holds the target and reset foils and controls the distance between the two with a piezoelectric motor. And here we have a summary of the experiment. First, data was taken with a neon-22 beam as calibration. First, to then determine the exact positions of the mini-ball detectors, and second of all, because the G factor of the 2+ state in neon-22 is very well known, and a TDRIV analysis of this data would yield the plunger zero offset distance, which is an important parameter for the TDRIV method and would be needed for the magnesium-28 analysis. On the right, you see the Doppler corrected energy spectrum for neon and the particle energy versus scattering angle matrix from the CD detector compared with LISE++ calculations. Then for magnesium-28 data, of course, there was the expected high rates of germanium detectors from beta decay activity. And maybe the biggest problem that was experienced during the experiment was that the first two segments or rings of the CD detector, the innermost rings, were damaged in the previous experiments and were covered entirely in the present run. And that means that a lot of magnesium-28 ions were implanted in this shielding and contributed to the increase of gamma ray activity without being useful for the gamma particle angular correlations. And in addition, there was a significant amount of silicon-28 contamination in the beam. So with this, we can continue to the results, starting with the calibration measurement on neon-22. Here we have the experimental ratio function and the best fit of the data in red. And the G-factor value that we obtain is 0.45, which unfortunately does not agree with the adopted value from literature. And we can make a comparison for neon-20 and neon-22 and experimental and theoretical predictions. So for neon-20, we see that the adopted value fits very nicely with different theoretical calculations, while for neon-22, the adopted value actually lies 4 sigma away from the theoretical predictions, and our present result actually lies above the theoretical predictions. So we need to examine these things a bit more into detail. Regarding our present result, from the fit we also obtain a zero offset distance for the plunger device of 2 micrometers, which is incredibly small and would be very, very difficult to actually achieve experimentally. So one would assume that a larger value of the plunger zero offset would be more realistic, and when performing a fit with a larger value, this would reduce the G-factor result, so it would bring it closer to the theoretical predictions. As for the adopted value, in the original publications, there were some questionable assumptions made on the charge state distributions of neon ions, and in addition, there seems to be a discrepancy that is observed in transient field measurements. And now is the point to make a small detour into the transient field method. So on the left you can see a typical setup for the transient field method. Once again, we first populate and spin orient the excited state of interest in the first layer of the target, after which the excited nucleus passes through a ferromagnetic layer which has been polarized by an external magnetic field. And as it passes through the ferromagnetic layer, the ion can capture and be stripped of polarized electrons multiple times, and it experiences a net magnetic field known as the transient field, which is again in the order of kilotesla. Each time an electron is captured, once again the nuclear spin couples to the electron spin and you have a precession, but it continues for a very short duration before the electron is stripped again. So in the end you have a net effect of a small deviation of the nuclear spin, and if one can measure the small deviation in the nuclear spin, so again through the angular distribution of gamma rays, one can determine the G-factor of the excited state. The problem with this method is that the transient field strength cannot be calculated from first principles, and instead some parameterizations have been developed for this transient field strength, which are applied in different ranges of the nuclear chart. And in general, the transient field strength is dependent on the z of the ion and the velocity of the ion as it passes through the ferromagnetic layer. And these parameterizations are a main source of systematic uncertainties in the transient field method, and usually because of this, the method requires that a calibration measurement is also performed on a different excited state with a known G-factor from measured by a different method. So now with this in mind, we can return back to the neon case. And on the left, here in bottom left plot, you can see the velocity dependence of the transient field strength from measurements on neon 20 and neon 22, which are calibrated using the adopted G factors of the 2+ states in these nuclei. And in the transient field parameterizations, there is no dependence on the neutron number, so in principle these two curves should be identical. However, there is obviously a discrepancy between them. And in fact, if we increase the G factor of the 2+ state in neon 22, we could be able to resolve this discrepancy, and we would bring the G factor of neon 22 again closer towards the theoretical predictions. And curiously enough, there has been a third measurement of this G factor, once again from the 70s, which is actually in agreement with the modern theoretical calculations, but it was neglected back then, mostly because of its larger uncertainty compared to the value that was in the end adopted. So the main conclusion is that we are left with no calibration for the plunger zero offset for the analysis of the magnesium-28 data. And speaking of which, here we have the experimental ratio function for magnesium-28 and the best fit of the data, which yields a G factor value of 0.8. And as we can see here in the comparison to the shell model expectations, it fits well with the pure SD shell calculations. Since the value that we obtained is quite reasonable, we consider that the test of the feasibility of the TDRIV method on a radioactive ion beam is rather successful. However, with such a large uncertainty, of course, we cannot extract any nuclear structure information. Still, we can gain some more information, possibly if we plot the correlation between the G factor of 2+ state in neon 22 versus the G factor of the 2+ state in magnesium 28, and in this way factor out the dependence on the plunger zero offset distance. And we see this correlation here with the present result for neon 22 and the adopted value for neon 22. And what's interesting is that if we assume that the adopted value for neon 22 is correct, we are left with a very small G factor for magnesium 28, which is at the same value roughly as the SDPF prediction for the G factor of magnesium 32, which is known to be dominated by the PF admixtures in Truder state, and this is quite unlikely, and again suggests that the adopted value for neon 22 is most likely underestimated. And in order to obtain a final result for magnesium 28, we need to perform a new TDRIV measurement on neon 22 to get a precise value and resolve this discrepancy. And such a measurement is already planned and accepted to be performed at Ganil, where we would have about 3 orders of magnitude higher beam intensity compared to the beam intensity available at Isolde. And with this we hope that we will be able to get a very precise and accurate value for the G factor of the 2+ state in neon 22. And the experimental setup would consist of 12 exogram Clover detectors and the Orsay particle scintillator array, which is shown here, and is a particle detector that's being developed here at IJCLab, specifically for TDRIV experiments. And so far these two measurements I mentioned were both applied on hydrogen-like ions. However, the hyperfine field strength increases rapidly with Z, and after about Z equals 20, the hyperfine field strength is so large that the precession frequency becomes too high to be able to measure it experimentally. So in order to extend the applicability of the method to higher Z nuclei, one needs to use lower charge states, such as lithium-like ions or sodium-like ions. And this would possibly extend the range up to about Z equals 50. So far, only one measurement has been performed on sodium-like ions with iron 56, again here at the Auto facility in Orsay. And we have accepted proposal to perform a proof of principle experiment for TDRIV on lithium-like ions with a measurement on titanium-46 at IJCLab. And in preparation for this TDRIV experiment, we performed a charge state measurement of titanium-48 to determine the optimal conditions to maximize the lithium-like fraction of ions. So here we have a selection of measured G factors and theoretical predictions for them in the PF shell for titanium, chromium, and iron isotopes. And the G factor of the 2+ state in titanium-46 has been measured previously by the transient field method, which is the black dot with the black uncertainties. However, the authors of the study did not take into account the systematic uncertainties that are related to the parameterization of the transient field method, and after taking those into account, you end up with these green larger uncertainties. And still, even with the increased uncertainty, the G factor is not in agreement with theoretical calculations, as are also the two theoretical calculations not in agreement within themselves. So we hope that the TDRIV measurement on lithium-like ions on titanium-46 would give us some final answer on this G factor. So here is the facility at IJCLab, where titanium-48 beam was accelerated by the K130 cyclotron and directed towards the RE2 recoil separator. And here we have the schematic of the RE2. In the target chamber, there was a set of different beam energy degraders and foils of different materials to study the charge state distribution of titanium ions exiting these foils at different beam energies. And by changing the magnetic field of the dipole magnet, one could allow for different charge states to pass through towards the focal plane. And the titanium ions impinged on a thick gold foil here at the focal plane and scattered into 3 zinc sulfide scintillator detectors with silicon photomultipliers. And here you can see what the obtained data from the zinc sulfide detectors looks like as a function of the B row of the dipole magnet. We see the individual charge states of titanium-48 in blue, and those of a beam contamination of chromium-52 in red. And if we take the relative intensities of these charge states and plot them as a function of target material and exit energy, we can obtain these charge state distributions. And since we're interested in the lithium-like fraction of ions, they're marked here. And we can compare these experimental values for the lithium-like fraction to model predictions from the Civitz-Grande model in the LISDE++ with relatively good agreement between the two. And from the obtained data, we can make a decision on which target and reset foil materials should be used and what is the optimal energy of the beam after the target that will scatter into the particle detector. And from the charge state distributions, we can also obtain information and estimates of which atomic configurations would be relevant to the measurement with their corresponding hyperfine fields. And we can then perform more detailed simulations of the expected ratio function from the titanium-46 experiment, which is shown here. And with this, I would like to also summarize this part of my talk. I presented the first results from the third TDRIV experiment on radioactive ion beams, and we've discovered a discrepancy in the G factors of the G factor of the 2+ state in neon 22. So we proposed a new TDRIV measurement of this G factor at GANYU, which should hopefully happen this year. And after that measurement, we can finally extract a definitive value for magnesium-28, although it will probably remain with a large uncertainty. And then in the future, we can return to ISODE for more TDRIV measurements on radioactive ion beams. And in the not so near future, maybe we can think about also targeting directly the G factor of the 2+ state and magnesium-32 because at FRIP supposedly they might reach the needed intensity for such a beam for the TDRIV method. And we're also working on extending the method to higher Z nuclei, and in preparation for the first measurement on lithium-like ions, we perform the charge state measurement of titanium ions at T-vascular. And we have also accepted the proposal for a TDRIV experiment on sodium-like ions on chromium-54 at auto, and in the future, depending on what beams are developed at GANU, possibly we could perform a TDRIV measurement on lithium-like ions on selenium-72. And finally, to conclude the entire talk, I hope I managed to show you that magnetic moments of excited states can provide us with very useful information on nuclear structure. And the field of magnetic moment measurements is quite versatile, with a large variety of physics cases that are accessible, and there are different methods, detector setups, and analysis techniques. And as you saw, there are many plans for the future, and hopefully there will be a lot of interesting results soon. With that, I would like to thank my collaborators, and also thank you for your attention.